This is Lab 9 Diffraction.
For OPTI 380 under TA Lab New Year.
For part A of this lab, we looked at Fresnel and Fraunhofer diffractions as a laser traveled through our system. To do this, we adjusted the height of the Heaney laser to shine through a pair of lenses and into the sensor inside the far tube, turned on the sensor software to visualize the intensity of the beam and help with its alignment, and attached apertures to the second lens in order to get our diffraction patterns. The sensor tube would be moved far from the lenses until the Fraunhofer patterns could be seen, and then slowly closer until the Fresnel image was visible. For the single-slit aperture, we saw near ring-like fringes appear and then turn into a single line where it heavily saturated in the Fresnel. The double slit seemed to produce double the initial fringes, where they would begin to converge until becoming two lines in the Fresnel. For the square slit, the Fraunhofer showed a crosshair-like pattern and then became a solid square in the Fresnel, where the triangular slit created a similar pattern but with triangular geometric properties. Finally, the circular slit produced a large circle in the Fresnel and a smaller circle surrounded by visible waves in the Fraunhofer. This pattern would be recorded and plotted into MATLAB using the provided code, which allowed us to view its complex data. The patterns closely fit what you'd expect from the sinc and sum functions until the peak. This is likely due to some of the complications we had with the polarizer we used in our system to create clear images.
In part B of this lab, we measured the divergence angle, beam waist diameter, and numerical aperture of the laser. To do this, we used a beam profiler to measure the diameter along two axes of a helium neon source laser. The profiler was placed as close as possible to the exit of the laser, and the diameters were recorded. We then moved the profiler back by 3 centimeters and recorded again. This was done until we reached 45 centimeters. Using Python, we fitted a Gaussian beam to our data, which we then plotted. We found the output of the profiler to be extremely noisy and unstable, which is reflected in the quality of our data. We found a beam waist diameter of 0.738 millimeters for the major axis and 0.726 for the minor axis. To find the divergence angle and numerical aperture, we will be using the value for the major axis as they are very similar. In the far field, the beam equation can be simplified as shown, and we can find the slope of the beam expansion as W0 over ZR. Using trig, we find a beam divergence angle of 0.0625 degrees and a numerical aperture of 5.5 times 10 to the minus 4.